All the AI we use every single day, the chatbots, the camera on your phone, it all feels like it just appeared out of nowhere. But it didn't. It's actually the result of two huge Big Bang moments. Today, we're going to break down the two revolutions that truly created modern AI, the one that taught computers how to see and the one that taught them how to understand us.
Okay, so let's get right into it. If you really want to understand the AI of today, you have to ask, what were those Big Bang moments? Well, there were two of them. One gave machines sight, and the other gave them a grasp of language. Let's start with the first revolution.
So, our first story, our first revolution, kicks off in the world of computer vision. That's the science of teaching computers to make sense of pictures and videos. And for decades, let me tell you, it was a slow, painful, and honestly super frustrating process.
Before 2012, if you wanted a computer to recognize, say, a cat, you had to painstakingly hand-code the rules. You'd tell it, okay, look for pointy ears, look for whiskers, a furry pattern. It was so brittle. I mean, if a cat was in a weird pose or its ears were hidden, the whole system would just break. But after 2012, this radical new idea started to catch on. What if, instead of giving the AI the rules, we just showed it millions of cat pictures and let it figure out the rules for itself? That shift, though, that huge change in thinking, it needed one thing above all else.
And that one thing was data. A mind-boggling amount of it. This is where ImageNet comes in. It's this gigantic database, a project led by researcher Fei-Fei Li, with over 14 million images, all labeled by hand. It was the perfect digital playground, this massive sandbox where a brand new kind of AI could finally learn to see. ImageNet was the fuel, and the match was about to be lit.
And that match was struck in 2012 at the yearly ImageNet competition. A team from the University of Toronto, led by the legendary Geoffrey Hinton and his students Alex Krzyzewski and Ilya Sutskever, they submitted a model that would change, well, everything. They called it AlexNet.
This number, this is what changed the game. At the competition, AlexNet hit an error rate of just 15.3%. Now you might hear that and think, okay, so what? But you have to understand, the next best model, the runner-up, was at 26.2%. That is a huge difference. This wasn't just a win, it was an absolute blowout. It was the starting gun for a whole new era of AI.
So, what was AlexNet's secret weapon? Well, at its heart, it was a deep convolutional neural network. And the key word there is deep. Compared to everything that came before, this thing was a monster. We're talking 8 layers of neurons and 60 million parameters it could tweak and learn from. This depth is what let it learn these incredibly complex patterns in images, way beyond what anyone thought was possible. Which leads to the next question. How did they pull this off?
Right, so AlexNet's victory was basically a perfect storm of 3 things coming together. First, you had the massive ImageNet dataset to train on. Second, the team did something pretty clever for the time. They used powerful gaming graphics cards, GPUs, to do the heavy lifting computationally. And third, they used some smarter design tricks, like something called the ReLU activation function, which was way more efficient for training such a deep network. These 3 things, all at once, made the magic happen.
So AlexNet basically cracked the code for seeing. But there was another, maybe even tougher, challenge just over the horizon: how to understand the messy, complicated, and sequential world of human language.
Yeah, recognizing a photo is one thing, but language is different. The order of words changes everything, right? Dog bites man means something completely different from man bites jog. The AI models they had back then just couldn't handle that kind of sequential context. They really struggled.
At the time, the go-to models for language were called recurrent neural networks, or RNNs, and they had this fundamental flaw. They had to read a sentence one word at a time, in order. Not only was this super slow, but they had a terrible memory. By the time an RNN got to the end of a long paragraph, it had often forgotten what was said at the beginning. This was a massive roadblock.
And then, in 2017, a team at Google published a paper on a totally new kind of architecture, one that just threw the whole sequential one-word-at-a-time rulebook out the window. It was called the Transformer.
Now take a look at this diagram. What's really fascinating is what you don't see. There are no loops, no sense of things having to happen in a strict one-after-the-other sequence. Instead, the Transformer was designed to look at every single word in a sentence all at once. And it did this using a brilliant new trick, a mechanism that will become the core of the second AI revolution.
That mechanism was called attention. And the groundbreaking paper that introduced it to the world had a title that was bold,
perfectly descriptive and just awesome.
This was it. Attention is all you need. What a statement, right? It was basically a declaration of war on the old sequential models. The paper's big idea was that a model could understand language just by learning how to weigh the importance of every word in relation to every other word all at the same time.
And this right here is the engine that makes it all work: self-attention. I know, the diagram looks a little intense, but the idea is actually pretty simple. For every single word in a sentence, the model asks a basic question. To understand this word better, which other words in this sentence are the most important? It figures this out by creating a query for the word it's looking at, and then it compares that to a key from every other word. The better the match, the more attention it pays to that word's value, its actual meaning. And it does this for every word, all at once, to build this rich, interconnected understanding of the whole sentence.
But it gets even cooler. The transformer doesn't just do this once. It uses something called multi-head attention, which is like running that whole attention process multiple times in parallel. Think of it like a team of experts all reading the same sentence at the same time. You know, one head might be looking at grammar, another is figuring out who did what to whom, and a third is looking at the overall tone. It's this team effort that builds a much deeper, more nuanced understanding of the text. And this table from the original paper shows you exactly why it was such a home run. Just look at that row for sequential operations. For the old recurrent networks, the amount of sequential work goes up as the sentence gets longer, but for self-attention, it's a constant. It doesn't matter how long the sentence is. This was the key that unlocked massive parallelization on GPUs, and it's what allowed us to start training the gigantic language models we have today.
So there you have it, a revolution in how machines see and a revolution in how they understand sequence and language. Together, these two breakthroughs built the foundation for pretty much all the AI we interact with today. Seeing them on a timeline like this really puts it in perspective. 2012, AlexNet shows deep learning can conquer vision. Just 5 years later, 2017, the Transformer unlocks the same potential for language. Two game-changing moments only half a decade apart. The pace of progress was just incredible. And you can see the legacy of these two ideas literally everywhere. AlexNet's deep, layered design is the direct ancestor of the computer vision in your phone, in self-driving cars, everywhere. And the Transformer, it's not an exaggeration to say it's the blueprint for virtually every single large language model you've ever heard of. GPT, Gemini, Claude, you name it. These two breakthroughs are the reason AI exploded from research labs into our daily lives.
Which, of course, leaves us with one last, really interesting question to chew on. We've made incredible progress on seeing and on speaking. So what's the next great frontier? Is it complex reasoning? Is it giving AI a body to interact with the world? A true physical understanding of cause and effect? That's the problem researchers are tackling right now, standing on the shoulders of these two giant revolutions.